Good day. Today we're going to talk about regression. Regression shows the degree of correlation between two variables. For example, studying for a test. If you study for a test, you should make a higher grade. The way regression works, we take the actual time studied per student, we take the score they made on the exam, and we put that on an XY axis. X would be the hours spent studying, Y would be the score. After doing this with every student, we would create a regression line, a line of best fit, to see what the correlation is and how strong that correlation is between your studying hours and your score on the exam. What regression does, it allows you to predict or explain the variation between those two variables. You have a variable that is called the response, and that's what you're trying to explain or predict. So in my example, score on a test. The variable that is used to explain or to predict that response is the explanatory independent variable. The actual regression line is the line of best fit. So in these examples of a scatter plot, what a line of best fit is a line that goes in between half of the dots. Now this is called a weak positive linear relationship, because notice how far away the dots are from my line. Versus the second example, where they're close to the line, and the third example, they are extremely close to my line. A perfect one is a 1-to-1 ratio. Well, it doesn't have to be 1-to-1, but it has to be the same slope throughout to hit every point. Okay, that's what the relationships are. No relationship would be like the seventh, 1, 2, 3, 4, 5, 6, 7, 8th diagram. In that plot, there is no line that I can draw and say, well, I know this is the line. That is the same as this as far as how many dots are on both sides. There is not a pattern in that relation. Now, the one thing you do need to be aware of is an outlier. An outlier is a point that does not fit the pattern of this scatter plot. So in this diagram, there is my line of best fit, close. But this point way down here is separate from every other point. It's nowhere close to that line. So in that example, it's the study hours and score of the ATAR. I don't really know what that is, to be honest with you. But the study hours were 26, but he only scored a 35. This student just failed the test miserably. There's nothing else that I can really say for that kid, except he is an outlier according to that relationship. Now, there are 5 different types of models for best fit that we will be using in Math 4. Linear, quadratic, exponential, logarithmic, and sinusoidal. Now, I do realize there are more transformations than what I have listed in these problems. Math 4-wise, we are good at just these, okay? All right. Using a calculator, you can determine that line of best fit. To figure out how close this is to the line, how strong this correlation is, you look at the R squared value. Now, R is the distance, the average distance of your points from the line. R squared is that correlation. Desmos will do that for you, and I'll show you how shortly. Determining the line of best fit. For the problems below, find the equation for the line of best fit and use the R squared value to determine if the correlation is strong or weak. Determine the correlation coefficient and the line of best fit. X is the year, Y is life expectancy. So I'm going to open Desmos. Click the plus table, and I'm going to type in the years. 1900, 1910, and I have a pattern going by tens, so 30, 40, 50, 60, 70, 80, 90, 2000, and 2010. All right, 47.3, 50, 54.1, 59 that is not a 9, 59.7, 62.9, 68.2, 69.7, 70.8, 73.7, 75.4, 76.8, 78.7. Now let's go ahead and type in all of our lines of best fit. Y1 tilde M X1 plus B. This is a lot faster to do on a computer. Now, I do not care right now about that actual graph. I'm going to hide it. The only thing I care about is having every one of these listed in. So Y1 tilde MX1 plus B. That is linear again. AX1 squared BX1 plus C. There's my quadratic. Again, hiding that. Y1 tilde A times B of X1, click the right arrow, plus C. Y1 tilde, that was my exponential, now I do logarithmic. A times the ln, natural log. You can technically put log for log. Truthfully, it doesn't matter. I prefer ln. I'm lazy and don't want to have to type as much as log, so I take off one letter. Anyway, plus b. Lastly, my sinusoidal function. Once again, there's when you actually do have two different ways to write. You could use cosine. However, I am partial to sine for these problems. A times sine of B I like putting an extra parenthesis here to get the horizontal translation easily. Plus C plus D. Okay, there's all my functions typed in. Now I'm going to hide that for a minute. And I'm going to change the domain and range of this graph because I want to fit this model. I'm going to start in the year 1850. That's a little bit less than 1900. And I'm going to stop at 2050. For my y-axis, I'm going to start at the lowest at 40 and up to 90. Now the reason why I like doing this, I can look and get a pretty good idea of what this graph needs to look like. Now, I'm going down through these functions and I'm looking at the r squared values. So for the linear, r squared is 0.9565. So I'm trying to beat that r squared. That's a good correlation. Let's see if there's a better. Quadratic is 0.9928. That's the new winner. It's beating the exponential, it's beating the logarithmic, and it is tied with the sinusoidal. So let's look at these two graphs. They are almost identical. So you have a choice. Which one would you like to use? Now I'm choosing the quadratic because, again, it is less to write and I don't feel like having to write stuff that I do not have to. So y equals, pay attention to something. When you're coding in Desmos to get this, you put y1 tilde and use x1s. For the equation, y equals and regular x's. So y equals negative 0.00185534 times x squared plus 7.53731 x. I'm going to write that 7. It's not spaced correctly. Times x minus 7,583.8864. Do I need all these decimals? Yes, I want every one of these decimals, because if you round them off, you could very easily get another one of these functions as a stronger line of best fit, and the r squared value, that correlation, can change. Now what is the strength? Well, r squared is equal to 0.9928. This is a very strong line of best fit. If the r squared value is 1, it is perfect. Now, I'm looking through the rest of your problems to see if there's anything that'll throw you for a loop. I'm going to get you started on number 5, and I'm going to let you do the rest, including number 5, but I'm going to get you started. Number 5, I'm given a scattered plot with these coordinates. I'm not given a table, I'm given a graph. So I have to go through and write them by hand. So 0, 63 is my first point, 170, and so forth. All right, try these example problems. Pause the video, and I'm going to show you the answer key. All right, that is all that I have for you today. Have a great rest of your day, and I look forward to our next lesson.